Good morning, everyone. First of all, thanks to the organizer for having me here. It's a very nice community, and I've learned a lot, and I'm so glad to be here. So I'm Jongseok Lim. I know it's very challenging to pronounce my name, but it's fine. And so I will continue to talk about the electron EDM measurement that is happening at Imperial College. And I will focus on our future direction that is using ultracold molecules. Okay, so as we know, the standard model of particle physics is one of the most successful theories in physics. It classified every elementary particles and explained their interactions with amazing accuracy. So there were hardly any problems, but now we know this applies to only a small fraction of the universe. So 95% of the universe is made of dark matter and dark energy, but the standard model gives no explanation what these are. Also, quantum field theory says that there must be almost equal amount of matter and antimatter in the universe. So Sakharov pointed out in this paper that this matter-antimatter asymmetry requires violation of CP symmetry. So there is CP violation in the standard model, but that is far too small to explain the observed matter-antimatter asymmetry in the universe. So these observations make a strong argument, statements, which is new physics with new forces and particles are waiting to be discovered. And one way to discover the new particles is obviously to build a huge accelerator and try to make the new particles directly. And there is another promising and ingenious way, that is using electrons as a sensitive probe to new particles. As you know, there are some new theories that tries to go beyond the standard model. And one of the generic features of these new theories is that they assume there are new particles carrying CP violation. And the new source of CP violation induces asymmetric charge distribution around the electrons. So it will be looking like this. So there are relatively more negative charge on one side than the other. So it has electric dipole moment. And we call this EDM. And if EDM exists, then it must be aligned to the spin axis. Otherwise, there will be additional quantum number, and the world we see will be very different. So now the question is, how big the EDM would be, and how can we measure it? As Tanya explained, the standard model predicts extremely tiny value. So it's in the unit of electron charge times centimeter. So 1 unit of each centimeter means like 1 electron is displaced by 1 centimeter. So looking at these numbers, maybe you can guess how small it would be. And on the other hand, the theories that tries to go beyond the standard model predicts much bigger values. So these are some predictions from the supersymmetric theories. These are non-SUGI models. And the message here is there is a huge gap between these two predictions. So EDM search can be a clean window to the new physics. And also the EDM sensitive size, DE, is inversely proportional to the mass of the new particles, lambda. So achieving better EDM sensitivity allows us to explore a higher energy range of the new particles. And conceptually, this is the way that we measure the EDM. So this sphere is again electron, and this purple arrow is its spin. And if magnetic field is applied, then the spin precesses at some rate. And if electric field is applied together, then due to the interaction between the EDM and the electric field, the precession rate is changed. And if we measure for the reversed electric field, then and by the difference between these two cases is proportional to the EDM size, right? So we can measure the EDM. And in here, we want to apply electric field as strong as possible. And this is why we use heavy polar molecules, as Tanya said. So it is shown in these two papers that the effective electric field that the electrons experience inside polar molecules can be enormously enhanced. That's basically because the polar molecules can be easily polarized by applied electric field. And in YBF, it's about 1 million times. There have been some experiments to measure the EDM using heavy polar molecules. And so far, all these measurements were consistent to 0 within the sensitivity of this experiment. But if we convert this sensitivity to the mass of the new particles through this equation, then it already exceeds the kinematic energy width of Large Hadron Collider. So therefore, these experiments give tight constraints to the new theories. And even more, we have been building a new machine which can improve the sensitivity to here, that's using ultracold molecules. Okay, so if we have this sensitivity, we can test both of the new theories. And if we find a non-zero EDM, it's fortunate thing, then it will be a direct evidence of the physics beyond the standard model. And to give you more understanding of our experiment, I will explain the procedure that we take for the EDM measurement. So the whole EDM measurement happens in the absolute ground state of our molecule, YBF. It's electronic ground state and vibrational ground state and rotational ground state. And in this level, there is this simple high-fine structure. And the whole experiment is to measure the energy splitting between these m equals +1 and -1 states. And here I use the notation plus or minus states to express these superposed states. And the basic method is simple. So we prepare the molecules in the plus state, which will evolve to cosine phi plus I sine phi minus state, where the phase phi has two parts. One is the magnetic part due to the interaction of the magnetic dipole moment and the magnetic field, and the electric part, which is due to the interaction between electron EDM that we want to measure and the effective electric field. And of course, phase phi evolves, is proportional to the coherence time, which I use tau. And in YBF, with the typical electric field that we apply, which is a bit bigger than 50 volts per centimeter, it's about 20 kilovolts per centimeter. The effective electric field is 17 gigavolts per centimeter. This is still pretty large. And after the phase evolution, we map the plus state to F0 state and minus state to F1 state. And then we measure the population in these two states by state selectively deriving this transition at 552 nanometers. Then the difference of the populations divided by the sum equals to cosine 2 phi. And you know, from this phi, we can extract the EDM size dE. So of course, there are some more complicated procedure, but basically by doing this, we measure the EDM. Okay. And this is the schematic of the previous Imperial's EDM apparatus. So YBF molecules are generated here in a supersonic beam. And we prepare the molecules in the plus state, and the molecules pass through a spin precession region where we apply precisely controlled magnetic field and electric field. And then we measure the population in the plus and minus states. So the beam is quite fast, and so the spin precession time was limited to less than 1 millisecond in this experiment. And of course, we want to make this spin precession time very long, but the problem is the molecular beam is divergent. So we can't make this region infinitely long because there will be any molecules left in the end. So what's the plan? So our plan is to massively increase the spin precession time by using ultracold molecules. And we think there could be two good ways. And one way is still based on the beam experiment. And here, the laser cooling in this transverse axis gives us a very highly collimated beam, which can travel for a long period of time without diverging. So there, and we believe that with the laser cooling we achieved, the beam precision time can be 100 milliseconds, which is 2 orders of magnitude bigger than our previous results. And there are many improvements in this experiment, but I will focus on this cryogenic source, laser cooling, and the interaction region. Okay, so cryogenic source. So this is a cell which we call bucket cell. It's about this size, and into which we flow some helium gas at 4 Kelvin. And pulsed laser comes through this window and ablates the ytterbium metal target and make a hot plume. And down this tube, we have SF6 gas, and all of these are mixed inside. And by the miracle of chemistry, we have YBF molecule. And at this time, the temperature is fairly high. It's a few thousands of Kelvin, but they collide with helium atoms many, many times, and they are cooled down, and they come out through this aperture, and we have YBF molecules. And by doing this, we have much slower beam compared to the supersonic source. And we have recently upgraded the cryo cooler. This can be cooled down to 1 Kelvin, and we have even slower molecules. And we are not satisfied, so we put additional deceleration stage here, which is looking like this. So this is originally developed by John Doyle's group at Harvard, and at the expense of some molecular flux, now we have much slower beams. So their mean speed is about 40 meters per second. And after optimizing some experimental conditions like helium flow or Young pulse energy or the size of this second stage, we now have about 10 to the 9 molecules per shot that are traveling slower than 40 meters per second, which is great. So this source is now working nicely and stably in our lab. Okay, the next technique is laser cooling. I'd say laser cooling of molecule is much more difficult than that of atoms. And you know, to make laser cooling to work, we have to have closed cycling loop. And here I show you an interatomic potential energy of the molecule in the ground electronic state and excited electronic state with their vibration levels. And in molecule, if we drive this transition, for example, then this state can be decayed to any of the vibrational levels because there is no selection rule for vibrational transitions. And so that means we have to repump all these vibrational levels using different lasers, which is a pain. But fortunately, there are some molecular species that have favorable branching ratio, such as YBF. So we don't need to have thousands of lasers, but just a few. And each vibrational level has, of course, rotational degree of freedom. And we are interested in the n equals 1 state, the ground state. And if we excite it to the n equals 0 state, then by the rotational angular momentum and parity selection rules, this state can only decay to the initial state. So it's rotationally closed, which is good. Okay, so this is a cooling scheme that we use for YBF. And so the main cooling transition is from the ground vibrational level to the electron excited state in the ground vibrational level. So again, this is rotationally closed, but this 93% of the time, this excited state decays to the ground vibrational level, but it can also decay to the higher lying vibrational levels with this branching ratio. So we repump these states by driving these transitions with lasers at 568, 565, and 585 nanometers using some different excited states. but I don't have time to go into the details. And its vibrational level have different hyperfine structure that they are spreading over a few hundreds of megahertz. So we generate sideband frequencies using AUMs and UMs. And so we generate 16 laser frequencies, and they are all combined into a single beam and coupled a single mode fiber and delivered to the molecule. And at the molecule, we divide the laser beam into two, and they are coming from each side to the molecule. The reason that we do this is because we use sub-Doppler cooling. The particular mechanism goes like this. So in our cooling transition, the rotational, angular momentum in the ground state is bigger than the excited state. That means there are more sub-levels in the ground state, and some are bright to the laser, but some are dark for any given laser polarization. And if the laser is blue detuned, then the AC stock shift is positive. So it goes above the ground than the dark stage, and the dark stage remains the same. And this AC stock shift is modulated in space because if the two counterpropagating laser beams have the same polarization, then due to the interference, it's modulated like this. And if the molecule was in the bright state, then it can scatter photons, then it can be pumped to the dark state, right? If magnetic field is applied, then these dark states can get back into the bright state through a Larmor precession. And this Larmor precession is most likely to happen when these two states are close to each other. And also, the molecule tends to scatter more photons when the intensity is highest, which is where the AC stock shift is biggest. And so, molecule tends to scatter photons at the top and can come back to the bright state at the bottom of the potential hill. So if the molecule is traveling in this laser field, then it scatters photon here and coming back to the dark state, and this process goes on, and the molecule loses kinetic energy. Okay, so this is the laser cooling setup. So the molecules are generated in this buffer gas source, and the molecules pass through a laser cooling region where we apply the laser cooling beams. So this pair of beams cool the molecules in this direction, in this figure, and an identical pair of the laser beams cool the molecules in the perpendicular axis. And after this laser cooling, we measure their spatial distribution using a camera. So where the molecules crosses with this probe beam, they give laser-induced fluorescence, which is captured by this camera. And this is what we see from the camera. So this purple arrow is where the probe beam is crossed with these molecules, but the molecules are actually spread over this whole figure uniformly. And so this is without the laser cooling, so that's why it's uniform. And if we apply laser cooling, then we see a bright circle in the middle, which is a clear signature of the laser cooling. So with these laser cooled molecules, now the molecules were spreading like this, but now the molecules are flying like this laser pointer or slightly smaller. So it's perfect for the EDM measurement. By looking at the size carefully, we worked out the temperature, which is about 100 microkelvin. And with this temperature, the molecules can fly for about 100 milliseconds without changing its size that much. And inside this bright circle, we have about 10 to the 6 molecules per shot. And the beam brightness is increased by any 300 times. Okay, the next challenge for us is to control electric and magnetic fields. And to polarize our YBF molecule, we need to apply 20 kilovolt per centimeter for this large area. And to do this, it might be natural to think to make this electric field plates made of metal. But the challenge here is the magnetic Johnson noise. So in metal, the electrons can move freely inside metal, and that thermal motion generates the magnetic noise, which is a problem for us. So we made ceramic electric field plates. This is alumina, and this is coated by titanium nitride. That is to reduce the amount of the metal. And this metal, ceramic field plates go into a glass vacuum chamber. Again, glass is chosen to minimize the amount of metal around. And these metallic parts are made of titanium, which has low Johnson noise. So with this construction, we calculate that the magnetic Johnson noise is equivalent to 1 times 10 to the minus 31 centimeter in a day, which is lower than the projected sensitivity, which is good. And also, this plate should be flat because we want to apply the electric field uniformly, and the flatness of the plates are also fine. We tested these plates, this pair of plates, at up to 20 kilovolt per centimeter, and we didn't observe any electric discharge, which is good. And when we reverse the direction of the electric field, there could be some leakage currents, which is a problem. It's below 1 nanoamps, but actually this test is limited by the resolution of the ammeter that we have. And we need to make this below 20 picoamps. So we built a picoammeter, which is about to be tested. And of course, we need to control the magnetic noise coming from outside. And to do this, obviously, we make a magnetic shield made of new metal. So this shield is divided into multiple parts so that we can wrap the whole vacuum chamber. And one layer of this shield is not enough, so we make 4 layers of the shield. With this shield, we tested this shielding factor, which is above 1 million over the frequency range that we are interested, which is good. And we measure the magnetic field using this magnetometer from QSpin. It's a commercial company, and it's about this size, and it operates in the room temperature. So it's a vapor cell magnetometer, and it has a superior sensitivity and nice noise floor. So it's about 20 femtotesla per root hertz in the range from 1 hertz to 100 hertz. And this is the noise that we measure inside the shield. It looks nice because considering it was first try, but if we measure the noise outside the shield and divide it by the shielding factor in the previous slides, then we expect it to go something like this. So something might be happening inside the shields, but we don't completely understand what's going on now. It could be just the magnetic noise coming from the shield itself, but we don't know yet. Anyway, we are interested in the low frequency range because we will reverse the electric field direction slowly. And if we reverse the electric field at every second, which is here, then I don't remember the exact value, but I believe this corresponds to about 10 to the minus 31 centimeter in a day, which is fine. But if we reverse the electric field at every 10 seconds, then it is here, then it's bigger than our project sensitivity. So it will reduce our EDM sensitivity in the end. So anyway, we are making good progress, and one of the plan is to make active cancellation outside. So they will suppress the noise in this low field significantly. Okay, in the remaining time, I will explain the next plan. So looking to the future, we have been building the next generation EDM experiment that is using ultracold molecules trapped in an array. So up to this point, it's fairly identical to the beam-based experiment, but here, the molecules will be decelerated by this laser slowing and then captured in a magneto-optical trap. We recently demonstrated laser slowing, but it's too early to show the results. Anyway, it looks promising. And we know how to capture them in a mode, which is demonstrated with a lighter molecule of calcium fluoride. And to further increase the number of molecules here, we use, as Gloria's talk on Tuesday, we will use a magnetic lens, and we will have more than 1 million molecules in the trap. And these molecules will be transferred to an optical lattice. With these trapped molecules, the coherence time can be as long as tens of seconds. And so it will enable us to achieve sensitivity lower than 10 to the minus 31 centimeter and explore new physics up to peta-electron volt energy scale. Okay, in summary, we developed a source of high flux molecules with speeds lower than 40 meters per second. And we developed laser cooling for YBF, which enables us to have long precession time. We built Long-Johnson noise interaction region, and this is working nicely. We need to make some more progress to control the magnetic noise, but we believe it will be done very soon. Also, now we see a clear path how to trap YBF molecule and use them for the EDM measurement. And finally, I'd like to thank to the fantastic team and generous funding from various funders. Thank you very much.
Thanks very much. Thanks for a great talk about technological tour de force. Very nice progress, Dima.
Thanks for the nice talk. I'm curious, when you made the baseline measurement with Q-spin, where did you do it?
That's a very good question. So it's inside the shield, obviously. It's not shown in this schematic, but there were electric field plates inside, and it was sitting outside it. But it was close to the innermost layer of the shield.
Okay, so it's still in the shield, but not in between the plates.
Not in the middle of the plate.
And that's the difference.
Yes. Well, for what?
Well, you showed the reference trace for Q-spin. Yeah.
Oh, this is the noise provided by Q-spin. It's the noise floor, so we can't measure any noise below than this using this Q-spin. And so if there were no noise, then we will measure this kind of curves.
So this must be in some big magnetically shielded room far away from the walls, right? Yeah.
I think it's not clearly understood, but so this is it's not due to our machine. It's just due to this magnetic noise. It's intrinsic.
I understand, but how is it measured?
Also, is the shield temperature stabilized or not?
Not yet, but it might be helpful. But
yeah,
we don't have clear evidence if it would be helpful.
I think I mean it would be very useful if you're fighting such problems to talk to the NEDM collaboration.
Is it due to the thermal, Johnson noise? Yeah.
Yes.
Yeah, definitely.
I have one quick question. At this level of magnetic field fluctuation, what would be your extrapolated precision goal which you would be able to achieve?
Oh yes, as I mentioned in the talk, it'll be. I mean, it depends on the rate that we reverse the electric field, and we were thinking to reverse it at around here. Then it's currently at somewhere between 10 to the minus 29 and 10 to the minus 30 in a day. But I'm sure we can make a good progress here.
So more questions?
Okay, very nice. I want to know what happens to the SF6 from your source. Does it propagate? Does it go away? And then a second question, which is probably very stupid. I'm missing something. Is do you need such a huge external electric field, or you just need it to polarize, and then the field that actually matters is the internal field, and then the internal molecular field?
Okay, so the SF6 in here, they just go away. I mean, we flow much smaller amount of SF6 compared to helium. So SF6 is not a problem for us in the end. It's like, and it's 2 orders of magnitude smaller amount than helium. The next question was about the electric field we apply.
Yeah.
Right?
So then, what happens to the helium then?
Helium is a problem at the vicinity of the cell. So if we do anything here, like about in 10 centimeter, then there will be collision between the molecule and the helium. So if we do laser cooling, then they will be lost. And so we do everything after some distance. And electric field.
Why do you need such a high electric field external? Does that field is the one that counts, or is it just the internal field of the molecule? That's the question for the EDM shift.
Right. So the reason that we apply 20 kilovolt per centimeter is to polarize YBF molecule. I think I might have some right here. So this is the effective electric field of YBF molecule as a function of applied field. So at 20 kilovolt, it's about 17 gigavolt per centimeter. I think it's.
I have a technical question. So looking at this glass tube that you showed, I suspect it's an isolator, right?
Isolated from what?
Electrical isolator.
Yes.
And now you have now you have 20 kilovolt voltages in there. And so if there's some electrons coming from somewhere, they'll be accelerated to 20 kiloelectron volts, and they will collect on the glass plate until it is charged up by 20 kilovolts.
Yes, it's isolated from the electric field plates, obviously, but it's grounded.
You ground the glass plate that is an isolator.
So I mean, the accumulation of the electric charge will be small in a given time. So I know it won't be complete, but
might be charging up slowly, but it will stop charging up when it reaches 20 kilowatts.
Yeah, that's a good point.
That's a strong field. Right?
Yes.
That's the same order field that you find.
Yes. Yeah. That's a good comment. We will consider that.
Yeah, so your projection for sensitivity is quite significantly increased from the previous measurement. Could you maybe say more explicitly which changes that you're implementing and how much they contribute to this increased sensitivity?
Right. I might have some more slides that are relevant as well. So yes, so we have 3 projects ongoing at Imperial. One is using the supersonic beam of YBF. With this, we think we can achieve 10 to the minus 29, which is 2 orders of magnitude better than our previous experiment. And in here, the improvement is with the improved state preparation and detection. So we rotationally cool molecule. That means we have more molecule in the EDM state compared to before. And we also detect them in the cycling transition. So we have about 100 times more photons in the end, and with some improved systematics. And at this stage, still it's a beam-based experiment, but we do laser cooling in transverse axis. so they don't spread out, and they are slower because we use pop gas source. And using this, the spin precision time is increased by 100 times. So it's the sensitivity is increased to here. And the last step is to trap them in a lattice and do the measurement. And here, obviously the main improvement is to use the trapped molecule. And the coherence time is another 2 orders of magnitude improvement from here to here.
I have in this context a direct question. You've brought now all these fantastic new technologies together. What is your timeline regarding the data taking on this experiment?
That's a very good question. So we have been planning to finish this by around this time, but due to the delay from COVID, we believe and we will finish this construction by March next year. Otherwise, we will face a serious problem with the funding, and then we will lose our team. Then we don't want to build. It's very difficult to build our team again. So this will start. I mean, the EDM measurement will start hopefully next March. Then it will take about a year. I mean, data taking, analysis, and checking the systematics.
Okay, I see. Okay, then we can continue in the coffee break. There's one last question, and then let's go for a coffee.
I just wanted to ask, from which company you got this magnetometer?
Q-spins. Q-spins. Sorry for my pronunciation, but